Hello everyone, my name is Zhiyang, and this is the recitation handout walkthrough for week 11. So with this recitation handout, it's a lecture review for molecular structure and organic chemistry. It is already been posted on the Blackboard. You can check it out. Then let's go ahead and start with the question number 1. Question 1 is asking you to draw the Lewis structure for these 4 compounds and indicate the number of bonding electron groups, non-bonding electron groups, electron group arrangement, and the molecular shape. For any of the questions that asking you to draw the Lewis structure, first determine which one is the central atom. The central atom is the one that has lower electron negativity. So for the first compound, carbon sulfur 2, the central atom is the carbon, and sulfur to sulfur around it. Carbon has 4 valence electrons, and each sulfur has 6 valence electrons, so totally 12 valence electrons. So in total, we have 6 valence electrons to use. And we put the carbon in the middle and 2 sulfur around it. Let's first connect them with the single bond. And then carbon right now has 2 bonds, so 4 electrons around it. It needs 2 more. So we can draw another 2 bonds to the sulfur. And now sulfur has each sulfur has a double bond, so totally 4 electrons, and cannot form any bonds, so which will become 2 lone pairs. And then that's our Lewis structure. Let's double check. Carbon has 4 electrons, so each of them form a bond with the sulfur, so totally 2 double bonds. And then sulfur, because each sulfur shared 2 electrons with the carbon to form the double bond, it has 4 electrons left. So those 4 electrons become 2 lone pairs for each sulfur. So this time, the number of the electron groups for the center atom, let me change the color. So right now for the center atom, carbon, it has 2 double bonds. So the number of electron group is 2. Bonding group also 2. So bonding group is 2. And carbon doesn't have any lone pairs for now, so the non-bonding groups are 0. And the number of electron groups are 2 and bonding groups are 2. So the electron group arrangement is linear. And since it doesn't have any non-bonding electron groups, the molecular shape is same as the electron group arrangement, which is linear as well. It's pretty obvious the carbon and sulfur has a linear shape. Okay. For the second one, the sulfur, similar idea. Sulfur has a lower electron negativity, so we put it in the middle. For 2 fluorines, each fluorine has 7 valence electron, and it can share 1 bond, 1 electron with the sulfur to form a bond. And sulfur right now has 2 lone pairs, and each fluorine has 6 lone pairs. That's the Lewis structure for sulfur fluorine 2. The number of electron groups for the center atom sulfur, we have 1 bond, 2 bond, 3 lone pair, and another lone pair. So totally 4 electron groups. 4 electron groups, the electron group arrangement is tetrahedral. And for the bonding electrons groups, 2 bonding groups. So 2 bonding groups, which means 2 non-bonding groups. And if the electron group arrangement is tetrahedral and there are 2 bonding groups, the molecular shape is bent. So actually, it's like that. These are 2 lone pairs. Okay. The third one. For the third one, it tells you the sulfur is the central atom. So just put the sulfur in the middle. And oxygen for fluorine. Let's first connect them with single bond. And then we definitely, the sulfur this time is violate the octet rule, but that's okay. And we know each sulfur has 7 valence electrons, and it forms a bond with the sulfur. So each fluorine right now has 3 lone pairs. And now the oxygen first, it can be like that. So 3 lone pairs and a single bond with sulfur. Or it can be like that, like this. It can form a double bond. With the sulfur. So this time, let's deal with the formal charge. So for this time, the formal charge of fluorine is going to be the same. But let's count the formal charge for oxygen. Oxygen has 6 valence electrons, 6 lone pairs, 1 bonding, so the formal charge is -1. And for sulfur, it has 5 bonding groups, so the formal charge is +1. So it's not pretty good. For the one on the right, the oxygen has 2 lone pairs and 2 bonds, so which makes it no formal charge. Same as sulfur, no formal charge. So the one on the right is the correct Lewis structure, and I'm gonna erase the one on the left. So once we have the Lewis structure, number of bonding groups. First let's deal with let's find the electron groups for the center atom. Sulfur. 1 bond, 2 bond, 3 bond, 4 bond, and another double bond. So the 4 electron groups. 5 electron groups, sorry. 5 electron groups, which will give you a trigonal bipyramidal. And there's no non-bonding electron groups, so the molecular shape is same as the electron group arrangement, which is trigonal bipyramidal. The last one is the two hydrogen and carbonate group. So the carbon is going to be the center atom. B has 3 oxygen around it, and then this oxygen has 1 hydrogen connect to it, and these 2 oxygen has 2 lone pairs. This oxygen has 2 lone pairs. That's the Lewis structure for the last one. And the number of electron groups for the center atom carbon, 3 bonding groups. So 3 electron group will give you trigonal planar. And there is no non-bonding electron groups, so the molecular shape is trigonal planar as well. That's question 1. For question 2, which of the following 4 molecules are polar? So for these 4 compounds, maybe like this one, this one, this one, and this one, you probably need to draw the Lewis structure. But for this one, we can definitely tell it's a polar one, because fluorine has the largest electronegativity. So it's definitely a really polar compound. Then let's see the other 3. For the first one, phosphorus, hydrogen 3. Phosphorus is in the middle and has 3 hydrogen around it. And we know phosphorus has 5 valence electrons. And each hydrogen now is satisfied with the octet rule. So those 2 electrons become the lone pair. So if it's a lone pair, for the center atom, phosphorus, 1 bond, 2 bond, 3 bond, and another lone pair. So 4 electron groups give you tetrahedral. But there's a lone pair, so only 3 bonding groups, which makes it become a trigonal pyramidal. Trigonal pyramidal. And if it's become a trigonal pyramidal, it's gonna be like this. With lone pairs above. So that's why this is the trigonal pyramidal. And phosphorus has the higher electronegativity, so each bond will have a polar dipole moment like this. So we'll have a total dipole moment towards above. So it is the polar one. For the second one, oxygen in the middle, 2 fluorines, and still oxygen right now has 2 lone pairs. So 2 lone pairs 4 electron groups, right? So 1 bound, 2 bound, 3 pair, and another one 4. So 4 electron groups, tetrahedral, and 2 lone pairs, so 2 bonding groups. 2 bonding groups give you bent. So if it is a bent, it's like that. So each one will have a polar dipole moment towards the oxygen. So the net dipole is also towards above. So it is a polar one because the dipole moment doesn't cancel out. There's still a net dipole moment for this molecule. And for the last one, the sulfur in the middle, 3 oxygen around it. And in order to reduce the formal charge, each oxygen will form a double bond with the sulfur. And so right now the formal charge for oxygen is 0, and for sulfur is 0 as well. So it's like that. One, two, three. So 3 electron groups. No non-bonding groups. So it is a trigonoplanar. If it's a trigonoplanar, then it's on all of these 4 atoms are on the same plane. So the dipole moment can cancel out, right? So it is a non-polar. And we already figured out this one is a polar. So that is the correct answer. For question 3, we're gonna draw the Lewis structure for first acetic acid and phosphoric acid. For the acetic acid, the molecular formula is carbon hydrogen 3, carbon oxygen 2, and hydrogen. This tells us this our group. This is another group with a hydrogen. So by drawing that, first we know this carbon will have 3 hydrogen connect to it, and then we have this carbon. Let me use another. This carbon oxygen 2 will give you like that. And since this oxygen has lone pairs, it can attract this oxygen to form like that. And add the lone pairs. That's the Lewis structure for acetic acid. For the phosphoric acid, the molecular formula is hydrogen 3, phosphorus oxygen 4. Phosphorus is in the middle, and then three hydroxyl group around it. So at the lone pairs. Sorry, missed one. That's the Lewis structure for the phosphoric acid. For question 4, it's just asking you to draw the deprotonated and deprotonated. So if this is a Lewis structure for acetic acid, if it's gonna protonate the proton, which is this hydrogen, it's gonna become like this. Since it's deprotonate a proton, so this oxygen has 3 lone pairs around it. So this one have a negative charge. To form a resonance structure, one lone pair come here and break these double bond to it to form this stuff. And for the phosphoric acid, if it deprotonate a proton, for example, let's protonate this one. These 3 hydroxyl groups, they are the equivalent, they are the same. So either of them is fine. And then it's like that. Right? And this lone pair can come up here to form a bond, and right here is a double bond, so it can go back to the oxygen to form this one. Okay, that's question 4. For question 5, draw a Lewis structure for ethanol. Label the molecular shape around the 3 center atoms. Ethanol, the molecular formula is carbon hydrogen 3, carbon hydrogen 2, oxygen, and hydrogen. So basically 3 groups. Like that. And label the molecular shape around 3 center atoms. We have 3 center atoms here. For the first carbon, it has 3 oxygen and another carbon-carbon bond, so totally 4 bonds, no non-bonding electrons. So it is a tetrahedral. For the second carbon, 1 carbon-carbon bond, 1 carbon-oxygen bond, and 2 hydrogen connect to it. So still 4 bonds, no non-bonding groups. So still a tetrahedral. For the last one, this oxygen has 2 lone pairs. So 4 electron group arrangement. It's 4 electron groups and 2 non-bonding electron groups. So it is a bent. And part B, on the drawing above, add a sodium ion positioned correctly to undergo ion-dipole interactions with the ethanol molecule using a dipole arrow to label the important dipole. So, undergo ion-dipole interactions here. This one has a oxygen, and we know oxygen is really electronegative compared with the other carbon. And since sodium has positive charge, so the sodium is going to be here. This is a dipole moment for actually let me start with this way. So for this molecule, the oxygen is more electronegative than the other two carbons. So the total dipole moment is like that. So towards the more negative for the oxygen side. And since sodium has positive charge, it will be closer to the oxygen. For part C, on the drawing above, sketch a position that the sodium ion could move to next to experience ion-induced dipole interactions with the same ethanol molecules. Similar idea, if this is a molecule and it has, since the oxygen is more electronegative, so it has this dipole moment as well. So we can just put the sodium this way, just around the oxygen. And that's right. The last question, part D. Draw two ethanol molecules experience hydrogen bonding interaction. I'll just draw the easier way of the ethanol. Carbon oxygen. If there's a oxygen hydrogen. So if there's a oxygen, let me actually draw it more obvious. So if there's a hydrogen has a bond, why I keep saying, well, if there's an oxygen have a bond directly connect to a hydrogen, then this is going to be a donor. And if there's another ethanol molecule to it, this hydrogen can have some interaction with the other oxygen. So this is the acceptor. And this is the hydrogen bond. So always remember, hydrogen bond is not a bond. It is a interaction. And on the right, draw two ethanol molecules positioned to experience induced dipole-induced dipole interaction. So the dipole-induced dipole interaction, induced dipole-induced dipole interaction is also called the dispersion forces or the van der Waals forces. So it's actually like a interaction, or the attraction between each two compounds. So for this interaction can be in any orientation because there can be a small instantaneous induction of a dipole in the molecule in any orientations. So you can draw anyway. As long as they are close, there will be a London dispersion forces or van der Waals between them. Okay. So that's all for the walkthrough for this recitation handout. If you have any further questions, you can either email those two supervisors or email your TAs. Thanks.